In this second screencast on integration in polar coordinates, I'm actually going to do some integration. So here's a typical kind of problem you could be asked. Compute the integral of the following function over the disk x squared plus y squared is less than or equal to 4. So the first thing to note is that this function is not given in polar coordinates, it's given in Cartesian coordinates x and y, as is the domain of integration. It's also given in Cartesian coordinates. So the very first thing we have to do is we have to go over to polar coordinates. So what you would formally do, in this case it's rather obvious, but in some cases where it's not, you actually make the substitution for x. So x is r cosine theta, and y here is r sine theta. So at f of x, y, you make that substitution, and you'll get 64 minus 4 r squared cosine squared theta minus 4 r squared sine squared theta to the 1/2. Okay, so I just substituted in for x and y here, r cosine, r sine. And again, I know that's obvious in this case. You're going to get a minus 4 r squared to the 1/2. And I'm going to go ahead and pull out a 2 and give me, is that what I want to do? Yes, and that'll give me a 16 minus r squared to the 1/2. All right, so that, again, you should have realized that this is just going to be minus 4r squared in polar coordinates. You wouldn't have to go through this substitution. I just wanted to say in cases where perhaps it wasn't so obvious, you make the substitution and you arrive at something that in principle is a function of now r and theta. And many authors use this notation. They'll call this, you start with a function in Cartesian coordinates and you end up with a function with a new name in polar coordinates. I won't generally bother with this, but I just wanted to say that. Right? And in this case, of course, it doesn't depend on theta. About the domain, it's clear that this domain, in fact, I'm not even going to write it as a set. It's just clear that this is given by r is between 0 and 2, and theta is between 0 and 2 pi. So I'll assume you see that. So I have to integrate now this over this domain in using the formula for polar coordinates. So let's just do it. So the integral now is theta is 0 to 2 pi. I'm not going to do every step here because I just don't want to. R is 0 to 2, and then I have my function here to 16 minus r squared to the 1/2. Don't forget the r, dr, d theta, and in fact that r is going to be crucial here. Let's just go ahead and notice that this separates, so we can pull out the d theta here. 0 to 2. I'm going to combine that 2 there. Give me 16 minus r squared to the 1/2 to r dr. And you'll see how nicely this integrates. This I'll just assume you can see that that's a 2 pi from integrating this. Now here I'm going to actually have to integrate. Fortunately the 2r is essentially the derivative of this, so I'm going to get with a minus sign 16 minus r squared to the 3/2 evaluated between 0 and 2. Okay. Now, I think actually at this point I'm going to assume that you can plug this in, and I don't think I made any mistake in calculating this. I got it 8 pi over 3 32 minus square root of 27. That's the answer. Okay, let's not spending more time on that. Okay, so that's how you do it. So the main summary is that there are certain problems that you can see here. You have these combinations of x squareds plus y squareds, and the only way x and y appear here is in x squared plus y squared. And so when written in polar coordinates, the problem is going to be at least expressed in a relatively simple form. And in this case, it was actually by design as something that you can integrate rather simply and get an answer. So I want to go on to another example, a very important example, and that is you're asked to compute this double integral of this function, again here expressed in Cartesian coordinates dA. Now we haven't discussed improper integrals, that is to say integrals with the limits going to infinity, but hopefully you know how to do that and this won't lead to any surprises. So what we want to do, trick here is, in fact, to view this as in polar coordinates. So let's go over here and do this. Again, we'll be quick. The integrand goes over simply to e to the minus r squared in polar coordinates. That's clear. What about the domain omega? So omega here is all of R2. And how would you write all of R2 in polar coordinates? Well, theta is simple. Theta will go between 0 and 2 pi, or any other range covering 2 pi for theta. And what does r cover? R will go from 0 to infinity. Okay, so it'll be an improper integral in R, but I think you know how to do those, so that's our domain. I guess I'll go ahead and write it as the set of r theta. I didn't leave quite enough room. Set of r theta such that. Okay, so there's my integration region. So let's, now we can do it rather quickly. What we're going to integrate now is theta will go from 0 to 2 pi, r will go from 0 to infinity. We have our integrand, e to the minus r squared. Now we have our area element, r dr d theta. You'll see that this r was crucial here. That becomes, again, it separates 2 pi d theta, not to infinity, e to the minus r squared r dr. Again, the 2 pi you should see immediately. And then we have here e to the minus r squared. We need a 2 for this and a minus sign. So it'll be a minus 1/2, evaluated between 0 and infinity. Again, I'm going to go rather quickly here. So we can plug an infinity there. E to the minus infinity is 0. So we have 2 pi, we have a 0, minus, but that is, there's a minus there, so that becomes a plus. At 0, it just becomes a half. So the answer is pi. Okay, I'm going to put box around. That's quite an important integral we just did. So why is this an important integral? Because of the following reason. Suppose it was because the following integral is very important, and if you've done probability, I guess you've seen this. The following Gaussian integral, you want to integrate from minus infinity to infinity of e to the minus x squared dx. Okay, and this is called a Gaussian integral. So I'm getting rather messy here. All right, so how do you solve this problem? Well, I'll just tell you there is no indefinite integral of e to the minus x squared. You can't write the indefinite integral of e to the minus x squared in terms of elementary functions. But what you can do is just call this integral I, and then notice that we can write I squared, I times I squared equal I times I, as the product of two of these integrals, e to the minus infinity to infinity, e to the minus x squared dx, times another one. Now I'm going to give this variable a different name, and that name I'm going to give it is y dy. I can now put these two together, e to the minus infinity to infinity, e to the minus infinity, infinity, e to the minus x times e to the minus y is e to the minus x squared plus y squared dx dy. And that is, if I didn't run out of room here, that is the double integral over all of R2 of e to the minus x squared plus y squared dA. That is the integral that we just did. You got an answer of pi. Okay, so we know the answer here is pi. So that's equal to I squared. So if I squared, let's just do it here. I'm going to do it in yellow. I'm going to switch. If I squared is equal to pi, then that gives me I is equal to the square root of pi. And that is how you integrate to this integral. That is how you compute the Gaussian integral. By converting it, essentially, if you start with this, do this I squared business, get it into this form, and then you convert it into polar coordinates, which is what we did here. We converted it into polar coordinates, and this r that comes about from the polar coordinate area element is what saves you and allows you to integrate this e to the minus r squared. All right, so quite an important integral and a quite important little trick there. And that's what I have to say about integration in polar coordinates.